right, welcome back. Now I'm recording, and now the fun will really begin, right? Because it is time to see you all again. It's time for some structural equation modeling, something like that. Any questions about anything that happened in the last week or so? 2 weeks. It's been 2 weeks. Time flies. Since we last met?
So are all the meetings pushed back basically all week?
Yeah, I will have those updated on the course website.
Okay.
Yeah, so that don't the course website will have all the updates. I don't touch the syllabus after I make it. So course website's a living syllabus, right? So it should all be current there. And actually, that means I need a lecture this week. So do you remember what we talked about before the break? Your break, my break? Oh, there's no break. We're working. You remember all this? Path analysis. Like, why did Jonathan put path analysis here? And I think we remember a little bit about path analysis. We at least got into, of course, this is just not intuitive going on today. Here we go. All right, now we can see a lecture screen. Here we go. You remember the path model, the motivation for it, right? We wanted to see how mathematics performance and perceived usefulness of mathematics is related to a person's belief in that they can do math, right here, and some self-concept as a mathematician, and those two are related to how much math you've taken in school, high school, and college, and potentially gender stereotypes as well too. That was the start. We started diving into that, and we had a great discussion of multivariate normal, of how the math works a little bit, and then we got into the worst part, which was model fit. But model fit took a while. The good news is model fit is the same here as it is in the measurement model. So all that time that we would normally spend in factor analysis taking this. So if you've seen Lisa's classes from before, she'd have this in the factor analysis section. I've just moved to the path analysis section. We're talking about the same stuff, right? Same stuff. What do you think of all this? Any questions? You like this process? I'll tell you what is difficult about it. I'll tell you what I don't like about it. Is that it may never feel like you'll get a model to fit. And I'll give you another standard. Depending on which field you're in, they might not even consider model fit, right? Like I was mentioning before, if you've got a machine learning system that's putting out a bunch of multivariate predictions, I don't believe anyone asks, does the model fit? They look at R squared. R squared doesn't do a whole lot though. I mean, you can get R squared, that's nice for prediction, but it doesn't tell you whether or not the model is actually accurate. And I have a great idea for this, for why or how this works. I'm gonna give you an example. Yeah, question? Oh, you mean the estimation process?
Yeah.
Those are very accurate. And I mean, we know a lot about numerical stability. Where those become inaccurate are when you're like, oh, I know how to use R and I code it. There's a few catches in how we do, like, in basically inverting a matrix and taking a determinant of a matrix takes a little extra care. But generally speaking, we've been good at that since the space program started in the 60s. I kid you not, a lot of the mathematics that go underneath these systems rely upon matrix algebra packages, BLAS, basic linear algebra system, LAPACK. These were all developed in conjunction with the US government in the 1960s. They're open source, they're free. They run on Fortran, they used to run on C, they've been translated multiple times. So no, we're pretty good about that. There's always room for improvement though. But my problem is that sort of this weird thing, depending on where you submit your manuscript or your work with path analysis or structural equation model fit may be the thing that makes it disappear, or model fit may not even be considered. Depends on where you go. So in a univariate regression, because there's only one outcome, model fit is actually perfect because you're basically describing mean and variance with it. But from when we start having more than one outcome. Yeah. HLMs, multi-level models are a bit different. Linear regression, yeah. So if you do linear regression, you won't see the things that we're talking about here, where we talked about RMSEA and all these indices. We had this summary statistic. You won't see this for a linear regression with one outcome. But when you have two outcomes, you do. And it's the same, by and large. There's, depending on which software package you use to implement this, there are somewhere between 2 and 200 model fit statistics. But the ones I covered the last time, just to remind you what they were, I'll remind you. I'll go through them again just to refresh the memory. These are fairly what you will report. You report all of them, and then depending on who your reviewers are, they might want different ones or may not like the values you have. Does that help answer your question? Okay. So let's go through this again, right? This is a piece of model fit. We started here with model test baseline model. It doesn't actually say what that is. Does anybody remember what that one is? That one. Yeah, actually, model test baseline model is the uncorrelated. That's right. This one above it, right here, and this is an old piece of Levon output. So let me go back to the more new one. The one right above it. That. That's right. So this is the newer version of the output here. So what I was looking for and where I kind of threw me visually, and I'm sorry that this is so small. Let's make this a bit bigger. All right. User tests, model test user model. I was looking for the first label and it wasn't there. This model test user model compares your model to the saturated model. Now remember, the saturated model is what Lisa would call the answer key. It's what we want to say, if this model fits as well as the saturated model, basically you have really good model fit. This was an overpowered test statistic, right? This is something that almost always will tell you it doesn't fit the saturated model, and that's in part because these are, again, big joint distributions that are pretty easy to tell small deviations. We don't get a measure of effect size out of this, let's put it that way. Saturated model, that's right. Saturated model is where I'm sorry? Your model. Yep. So remember, saturated is where it's like you didn't run a model at all. It's like you're estimating every covariance, every variance, every mean, right? Your model takes all of those covariances, variances, and means and boils them down into a series of regression parameters, residual variances, actually regression parameters and residual variances, those things. So that's the main one. This one doesn't get looked at very often. This is your model versus the independence model. Actually, this is saturated model versus independence model. Model test baseline model. That's because your model test baseline model, that is anything correlated in your data? That's what it's asking, basically. Right? So what it's comparing is a model where all the means are estimated, all the variances are estimated, and all the correlations or covariances are equal to 0, versus the saturated model where all the means, variances, and correlations are estimated. So what this tells you is anything correlated? That's not really useful because almost always there's something correlated in your data. Mm-hmm. Mm-hmm. Nope. Yep. So baseline goes for ridiculous model. Baseline means, I believe, in this case, uncorrelated variables. To me, again, in most of your research, with people or data are coming from the same person, kind of hard to find things that are uncorrelated. Then this one doesn't get recorded very often. Then we get to user model versus baseline model. This is where these two indices do get reported a lot. Comparative fit index, CFI, and the Tucker-Lewis index, TLI, and they're robust versions. So which one do you pick from this? I would always pick the most robust, these ones down here. And then with this being an index, higher is better. CFI will run between 0 and 1. TLI can get some weird numbers in it for the way it's structured. But generally speaking, unless, now this is a really extreme case because we only have two correlations in our data. Actually, one correlation in our data, two variables, right? There's only one correlation. That's where it gets a little weird. The more data you tend to have, the more it becomes stable. But both of these we would want to say is bigger than 0.95 would be good for each. And again, with the mnemonic for that, with the index, we want an index to be higher. Any root that we see here for model fit should be lower, right?
Okay, I have a question on this one.
Yes.
This one, I'd say, I second compares it to the independent variable model. And that's because the independent variable model states that there are no correlated variables.
Right,
So we're
exactly.
essentially just truly testing.
That's right. Saying to the extent that which things are correlated, our model does a good job with them. Basically, it's comparing likelihoods of your model versus likelihoods of or chi-squares of the independence model. Then we get into log likelihood information. We often don't report this, but if you ever have to do a likelihood ratio test, this is where you'd form those numbers if you weren't using the ANOVA function in R, which you can just use. AIC and BIC are information criteria, and SABIC. These things are information criteria, these right here. What those do is tell you if you have non-nested models, which models is preferable. Remember, lower is better. So for any given statistic, you have an AIC for every one of the models that you estimate. The lowest one would be the one that's preferred. There's no standard error to it in a non-Bayesian sense. Now you get to Bayes, some of those information criteria have some fun standard errors. So you can talk about how much certainty you have, but not here. BIC and SABIC would be the same. And then which one to use, AIC or BIC? Normally we always use these. I don't see anyone reporting a sample size very often, but some people I guess want it, so it's there. The first two, the top two, AIC and BIC, this is the problem with information criteria. If you've used them before, you'll note that you may have 5 models and AIC says model 4 has the lowest value and BIC says model 2 has the lowest value. Right? Which one do you believe? Oh, it doesn't matter because whatever you believe, the reviewer will believe elsewhere, otherwise. Right? So these are not the best things to use. It's sort of like the last resort model comparison statistics to me. And then finally, we have a couple other values. We've got RMSEA, which is the root mean squared error of approximation. Now, this is comparing the likelihood of your model to the saturated model effectively. And these values, usually these go down to 0. We want this to be less than 0.08. This is really bad fit right here. We want this to be less than 0.08 or less than 0.05 for really good fit. And I would pick a robust value with that too. And you can even see you see these p-values that they list here. There's your breadcrumbs. Adequate fit 0.08. Back in the old days, that's what we used to say. New days, by the way, it's much more complicated, but I don't know how much that filters into what you do yet. And then RMSEA less than 0.05 is really good. Those were sort of the standards set by Hu and Bentler in a paper many, many years ago. Those standards are under review still now. We have different iterations of model fit. So the 0.05, 0.08 in your research career lifetime might change at some point. So just give flexibility to what that is. What it's changing to is something a little bit more dynamic. What we've learned recently in the last 5-6 years is that model fit statistics also depend on magnitude of values, parameters in the model as well too. And so it's not just and sample size. So it's not just as simple as looking at a uniform cutoff for each. That's a problem. But again, these are things that we discuss in the quantitative methods literature, multivariate behavioral research, psych methods, psychometrica. How long it takes them to go from those journals to the applied or substantive journals empirical journals that you might be publishing your work in, because most of you aren't going to be publishing in quant methods, like pure methods research. I don't know how long it will take, so we're going to keep this here in the interest of time. And finally, standardized root mean squared residual. That's basically an average statistic of how far off your covariance matrix is from your model. to that of the data, the saturated model. And this, if I'm not mistaken, this model fit indicator here came from a model where we almost completely destroyed what the covariance was. We put a really uncharacteristic restraint. Actually, we can see it right here. I want to say it was the saturated model. It says model 03, but I'm not trusting it. But anyway, okay. So that's model fit. That's where we ended up last time. And then we started diving into multivariate regression. Sorry to move fast here. Right here. We talked a little bit about some other values as well. I think we stopped around here, right? Or did we get to multivariate regression? I don't think we did. Okay. Oh, good. Good. Thanks. I should have been more prepared. 45. All right. So we have these four different models, right? The four models we have were, and let me, keep you from jumping around. Let me go back to the page where all those models were listed so that we know exactly what they are. We have estimated the saturated model. So we know from that model, the model fit should be perfect because it's comparing the saturated model with itself, with the exception of the comparison of saturated versus baseline model, right? Baseline model being independent. Then we, just to show how this worked with a small set of numbers, I made some constraints, right? These are illogical constraints once you see the saturated model looks like this, but each of these constraints is rooted somewhere in multivariate statistics history. How's that sound, right? We've got variance components, which basically estimates a single variance for the diagonal and no covariances, right? That would be as if you ran a linear regression and just dummy coded which variable was each, but you had one single error variance, right? This doesn't fit either because you can see the diagonal has a very big residual variance or variance for one of the variables and kind of small here, and this is sort of the pooled variance estimate in between them. And then we get to the independent variables where we give each of these variables a different variance, and you see those are right about the right values, but the covariance is pretty far off. And then finally, compound symmetry, which constrains there to be one diagonal and then one off-diagonal term as well. Which, again, why do we have these here? You don't need to remember these, but you may have run into these in other courses, particularly when it comes to linear models or repeated measures ANOVA. That's just a comparison. So let's see which model fit best using model fit statistics. All right, so here's what we have to do. We have to go and ask a series of questions here. I'm just going to leave this. So everybody can see this okay? That way I don't have to jump around as much. Excellent. Okay, so we have four models, and we know one of them is guaranteed to fit because it's the saturated model. It's the answer key, right? We wouldn't even run that model usually because it will do it for us, but this is a demonstration purpose for your guiding. We have to ask four different questions. First, we need to see, do each of these three model fits, do each of the three models fit? Excuse my language. Right there. And then second, of the ones that fit, which one is preferred? Right? So you can basically go eliminate the non-fitting models. All right. Let's do that. This is model 1. This was the variance components, right? Where there was a single variance on the diagonal, 0 for the off diagonal. Here we see following. The chi-square test up here, I'm going to look in the robust column. The p-value, so we have 2 degrees of freedom. Why we have 2 degrees of freedom is because basically we have 2 constrained parameters, 2 fewer parameters than the saturated model. And those parameters specifically are, we are not estimating the covariance between these 2 variables, so that's one of them. And we've constrained the variances to be equal, so that means we're not estimating both variances. We get another degree of freedom there. So what these degrees of freedom tell you is the number of parameters you are short of the saturated model, right? So we're 2 away from the saturated model. And our p-value is 0. So if we looked at this chi-square, what we would call this is a likelihood ratio test. The null hypothesis for that likelihood ratio test is that your model is equal to the saturated model, or fits as well as. The alternative is it doesn't. Or another way of putting it, that those parameter constraints are not valid. The zero, set to 0, 1's easy to see that's not correct. The p-value is 0, so we reject that null hypothesis. So what does that tell us? Does this fit? Does it not fit? It does not fit the saturated model. Get used to that. We're going to see not fitting the saturated model a lot. Now, model fit baseline model, that p-value is 0.018. That tells us what? That tells us it's likely there's at least if we use a 0.05 criterion for alpha, we would reject the null hypothesis. This is basically saying that the null hypothesis here is that the independent model, the thing that has 0 correlation, is equivalent to the saturated model. So with the small p-value, we would reject that null hypothesis. The alternative would be the saturated model is needed, or another way of putting it, those correlations are non-zero. So there's some correlation in the data. And that's here is where all the numbers go haywire. By the CFI and TLI, both of those tell us there's no way this fits. They're very bad. They should be up to around point. They should be up above 0.95. If you're reporting negative TLI, someone's going to tell you to check your work. That does happen. We don't care about likelihood ratio tests here. We don't care about AIC here. But let's take a look at RMSCA. RMSCA is 1. Don't let that fool you. It should be close to 0, right? That tells you it's very, very bad. This looks like it could be a CFI or TLI. And in fact, when I saw an RMSCA of 1 there, my eyes are like, that can't be RMSCA. That's CFI, right? So I did a double take just instantly. I don't know if you saw that. It was sneaky, but I tried. This would also tell you not good fit. And then the standardized root mean squared residual, this tells you how far off you are. You see this value is very close to that covariance that's set to 0, that should be estimated. That's telling you how far we are off of that covariance. And that also is pretty high. So, does it fit overall? Does not fit. Okay. How about model 2? Why do I have model 4? Oh, I've renumbered them differently. Okay. So here, model 2, this was the variance components model where each variance had a different value, but the covariance was set to 0. Right? And this is independent variables. Sorry, not variance components, independent variables. So here, this is interesting. We have the likelihood ratio test comparing our model to the saturated model, giving just about the same value as our model to the baseline model. Why are these two the same?
Because the baseline model is the saturated model.
In this case, it's close because the baseline model, the name of this term, where the variables are independent, is our model. Right? And so our model, compared to the saturated model is here, and the saturated model compared to the baseline model is here, right? So this is comparing saturated to our model, and this is comparing saturated to baseline. And baseline is ours, so therefore they're the same. Right? And you start to see this repetitively as you go through. So this tells us both the same thing, that yeah, we probably need that covariance to be estimated, not 0. How are we doing? Make sense? Okay? Again, CFI and TLI, you don't want to see zeros. Even negative 0 would be bad. Then we get into likelihood ratio. We're not paying attention to it. It's not there. Oh, well, look, the RMSEA is 0.115. Now, that's bigger than 0.08, but there is still a probability of a small chance. It's actually, you have a 7% chance that there's really good fit of this model. So that tells you how much certainty there is in the RMSEA. Pretty certain it's not good. And the standardized root mean squared residual now is 0.066, and that's sort of that's behaving a little bit more like we'd want it to. That's a number that tells us it's sort of like how far are we off on a correlation sense for that one variable that should be estimated. So does this model fit the data? Let's go with absolute sense or not. No, this is not good either, right? And why is it not good? because we put a 0 for a covariance where there should have been a number, right? And I'm making you think about this. You may think this has nothing to do with my data. That this is why when you start getting into model fit and it doesn't fit, you have to sort of forensically determine where the problem is. Yes, Jake.
When you say you would put a number there for the call, is that just
Estimate a number.
so we would have a estimate?
That's right. Yeah. I mean, we could put a number in there, but that's not advised.
I was just wondering, like in the code, because sometimes
Oh, yeah.
like the ones and the zeros.
There are no. Actually, I'm glad you asked that because there are odd places where we do fix values.
Okay.
Now, they're not usually in path analysis. They do show up in measurement models, and the space where they show up in measurement models, where you first see them, are in comparing groups, like group differences on items or by item bias, differential item functioning, measurement and variance of these techniques. So we actually set latent variable means and variances sometimes, and we free them sometimes. But often you don't fix a number most of the time. Unless you're in machine learning. I'm just going to keep on recording. I'm just kidding. No, I don't even know they do that yet. All right, let's go with model 4. Model 3, excuse me.
Which is
Actually should be model 4 because my numbers are off. This is what my life is like right now, folks. I'm sorry. This is the problem with my head at the moment. I got a lot of things in my life going on, and I'm trying to keep everything straight. This is the compound symmetry model, right? So this one right here, we know the covariance is going to be pretty close, but we should be off on the variances, right? And there's one fewer parameter in this model to estimate than the saturated model. What I mean by that is we have a covariance here, and we have a single parameter for each of the variances. It's like a pooled variance. So when we do that, let's take a look at its model fit. Its model fit right here. Make sure I'm in the right spot. Yes, I am. There we go. The likelihood ratio test. Based on the likelihood ratio test, does this model fit the data? No. Why? The p-value is small, so we reject that null hypothesis, and the null hypothesis says that your model fits as well as the saturated model. Right? So we'd say no based on the likelihood ratio test. We've seen this 4 times now. I'm not going to talk anymore about the baseline model. Right? It has nothing to do with your model. Every time you use the data, you're going to the same data, regardless of your model. This is going to be the same, right? So we don't need to talk about it anymore. Yeah, it's pretty redundant. The CFI and TLI, you don't want to see those numbers. And then we get down to RMSEA, that's really high too. You wouldn't want to see that. And the standardized root mean squared residual as well. So does this indicate our model here fits the data? No. So we actually have no model that fits the data. So we wouldn't actually go and use AIC and BIC because it turns out to use AIC and BIC, there's an implicit assumption that your model fits the data. And if it doesn't, you actually start to not have the likelihood ratio, the likelihoods itself function the way they do in a normal information criteria. So that's model fit. That's how we start looking at it. And we know things are wrong with our data. So the next section of the slides are how to investigate where things are wrong. And I've sort of been talking about this, flipping back and forth, where I said, look at the saturated covariance matrix, look at this model's covariance matrix, right? We compare those. The local model fit measures do that, but do so in varying levels of complexity, right? So local measures of model misfit are statistics that point to the location where a model may not fit well. Now that location is typically the covariance matrix. And why that's the case is this example notwithstanding, we rarely do constraints on residual variances, which would be the diagonal of the covariance matrix. And we rarely do constraints on the mean vector, right? That is our prediction, our means model for the means. So pretty much the only place where we put our model puts constraints on a covariance matrix, where our model's constraints show up are on the covariances of the covariance matrix, right? The off diagonals.
Can you repeat that? So we don't usually do constraints on the variance of the mean vector. Is that what you said? Okay. Perfect.
Yes, we do not really do things on the variance and the mean vector. So think of it this way. In this example, with this 2 by 2 covariance matrix, and we have two means, right? If we go, this toy example has nothing to do with your science. It's just playing with numbers, right? So if I went in there and said one of the means was 0, I would get bad model misfit. Well, we'd never do that. In fact, the means are taken care of by all of the fixed effects in our model and the intercepts in our models. That sort of makes the means seldom the place where model misfit happens. When you look at the covariance matrix, our model will imply what the diagonal is. But for us, for these models, we just estimated the parameter on the diagonal. And that in two of the models, it was close. It was good, like saturated in the one where each was estimated separately. And the two models was not so good. But generally speaking, what we do with those is we just don't put constraints on residual variances very often. Right? The only times that we may would be if we have explicit assumptions that there's homogeneity across, if there's a group, like a group variable or some other of those types of ideas, but we seldom do. It's the covariance matrix, the covariances, that start to be the problem, right? So what we're talking about here is really looking at a comparison of what our model says the covariance matrix should be versus what the saturated covariance should be. Right, that slide where I had all four of the covariances in, we were just sort of implicitly doing that with all the covariances. That's what this is about. This is opposed to the last section. At the last section, all the model fit measures there were sort of global estimates, right? How well does your model compare to saturated? How well does saturated compare to independent, right? And then summaries of that, like RMSEA, talking about how far off you are from saturated in your model, or standardized root mean square residual, which talks about how far you are off from the covariances themselves across all of them. Here, what we're going to talk about is specific values of that covariance matrix. This is really where, what you do with model fit is you start with a global, and if it doesn't fit, it's now data forensics. So you have to go into the local and say, where is the fit the problem? Because how you fix that problem comes from where it is located. Okay? So here, what are the local measures of fit? They typically come in two types. I should say misfit, because if these measures are 0, that means there's no misfit. And if they're bigger than 0, there's misfit. But those two versions are residual covariance matrices. Residual meaning, how far off are you? Let's take one minus the other and see how far off we are. And then the other is this cool thing called modification indices. This is, I mentioned last time a little bit about maximum likelihood estimation. I said there's actually 3 different versions of hypothesis tests. Likelihood ratio is where you fit a null and an alternative. You fit both. Walled is where you fit the alternative, with more parameters. And then there's this third one that we never think about much, called score. Right? That is what modification indices are. That's where we fit a model that has too few parameters. These go through the model statistics and say, you know that covariance that you set to 0? How much would the model improve if you didn't set that to 0? It's like these hypotheticals. Not what's happening. These things are pretty cool. I think they're pretty cool. Other people, including the person I live with, aren't so wild about them. I think she calls it my son. Like, Dad, quit using mod indices, all right? Cringe. Yes, exactly. Thank you. The reason why these things are hypothesis tests, and they're subject to a couple problems. They're usually fairly accurate if the model is in the ballpark of fitting, but if you end up looking at a lot of them, you potentially inflate. You're sort of capitalizing on chance, right? You sort of have a p-value, and if you look at 15 modification indices, all with a p-value of 0.05, it's like doing 15 pair comparisons with p-value of 0.05. Remember the idea from design of experiments, from post hoc mean comparisons, that if we do too many hypothesis tests, we sort of inflate our overall type 1 error rate. That's one of the issues with these right here. But for the residual covariance matrices, these come in different flavors as well too. Unstandardized, which just means take the covariance matrix that's saturated, take your model's covariance matrix and subtract them. That's just the difference. Unstandardized is a little bit unsatisfactory because a covariance we talked about last time is a weird scale. It's in units of y times units of x. It's like an area almost, right? And so because it's so hard to understand the units, an unstandardized, you may get a covariance, a residual covariance that's big and unstandardized, but when you look at it from a more, when you understand how, it may just be a reflection that both variables had really large variances, right? So the scale of it is not really comparable. And so that's where you get a couple different types. Standardized, which tries to basically look at, I'm going to make it an analogy here. It's like looking at difference in correlation. It's not exactly that, but let's just put it that way, right? Because correlation is a standardized unit. And then normalized, which goes a step further and takes that residual and makes sure it functions like a z-score. So now you can talk about from a normal distribution, how many standard deviations away from zero is this result. So I like normalized a whole lot. Again, you get into capitalization on chance on that because if you're thinking about, oh, I have a critical value, if the normalized value is like plus or minus, what's the critical value for 0.05 and the z 1.96 plus or minus 1.96 away is like you're doing hypothesis tests in each. So it gets into it.
I need two.
Plus or minus 2 is what I can't. I have to do 1.96. Yeah. That hundredths place is really important. That's exactly right. So I'm going to go through each of one of these. I talked about them before, but I'm going to give you some demonstration here. The residual covariance matrix. So our our estimated variance components covariance matrix had a 0 here in the off diagonal, and then values down the diagonal. If we took our saturated model's covariance matrix and subtracted this is what we would get, right? Close to 0 down the diagonal and a 6.847 in the off diagonal, and that's because that off diagonal value literally was 6.847, right? So again, standardized, unstandardized, actually, I know people call this raw. Sometimes I don't prefer that word, so we call that unstandardized. I like that better. Sounds more polite. Normalized looks a little bit differently. Normalized, the way we look at these numbers are like z-scores, like I just mentioned. So a z-score close to 0 means it's not likely to be off by that much. But this in the off diagonal is a z-score of 2.403, and that would say that this right here, that number is the culprit for why our misfit's happening, right? And if we have a lot more of those numbers, we have you're not. I'm going to guess you're not going to run a path analysis on 2 variables, but when you have many more, you might see 4 or 5 of these that are big, and each one of those you may have to address. Yes, question.
Yes. So thinking about these normalized,
Mhm.
I presume that's easy enough to do, like with grain.
Yep.
Okay.
Yeah. No. There's just a line of code. The beautiful thing about Levon is
It's
it's.
just normalized.
Yep. Yeah. There are, and all this. I'm sorry, I didn't have R to show you this on the side by side. But if you go to the syntax file, you will see under each of these models the syntax to do this, and it is one line of code, and it makes your life a lot easier, at least for me.
And this is essentially telling us, hey, you should estimate.
That's right. Or yeah, in our case,
Or you estimate.
yeah, and actually, as we get to the end of this lecture, it will be you should create some type of path between these variables, right? We haven't gotten there yet because path analysis, where the covariance comes from, is from those regression slopes. So this is telling us right now that we know that performance and usefulness have some non-zero relationship, but we don't know what that is. And so for us to fix our model, we'd want to address that. Good question. So this is the residual covariance matrices. Then we can look at modification indices. And again, this is one line of code, and it will spit out a bunch of information. Let me describe what this is. What this tells you is in Lavon syntax. Remember the Lavon syntax we went through a little bit last time? The double tilde says, I want the covariance between the variable on the left side and the variable on the right side. Now remember, we also use this for variance. It would be a variance if the variable on the left side is the same as the variable on the right side. Right? So this one is telling us what? Okay, it's saying the covariance between performance and usefulness has a modification index, MI, of 6.239. What this is a chi-squared test statistic. Right? It is a 1 degree of freedom chi-square test. So 1 degree of freedom, a chi-square with 1 degree of freedom, if you want the critical value, if you're thinking of hypothesis tests, God, it's been a while since I taught like frequentist statistics. Erica's smiling because you've been through the Bayesian with me, right? But what this is telling us, we would compare this to a 3.84. 1 degree of freedom, that's a critical value of 0.05. The chi-square critical value 0.85. So if this number is bigger than 3.84, we would say, oh, if we added that to our model, it would fit better, right? This is testing the hypothesis that this parameter is equal to 0. Right, so the null hypothesis that this is testing is this covariance is 0. With this being a very large value, or much bigger than 3.84, the p-value would be probably 0.01, something along those lines. So we may reject that hypothesis. We may say, oh no, it is different than 0. The next line here is the expected parameter change. That tells us what we think the value would be if we estimated it. Now this, you'll tell, is not, it's close. I think the value was 6.87, something like that. It's close to what it was. I never ever pay much attention after that right there. Because this right here tells me if I should add it or not. All these other numbers, some of those are useful in some contexts, but most of them are not for us. Augustine, and then I'll come to you, Michael. Yeah. Yes. In general, that's a good way of looking at it when you have one. The question would be, how many of these are you looking at? Right? And so you might say, so 3.84 is that alpha 0.05 level. But if we have, 20 of these statistics, all at alpha 0.05, overall our type 1 error weight will be inflated, right? It will be much bigger than 0.05. So what I typically do, and actually in M+, they don't even report these, I think, unless, or maybe they do now, but back when I used to use M+, the value was 10 before they would report them. So typically speaking, the larger the threshold you set for yourself to include that, the less you're capitalizing on chance. Basically, more evidence is needed statistically to say that the parameter is needed to fix the model. So if I could compare and contrast just a little bit, I have the other, I'm not even going to talk so much about scales and all this other stuff. Yeah, no problem. What's this? Me scale. Oh, it's not even here anymore. Yeah, no, sorry, I should have changed it. No, ignore these. Expected parameter change. This is, I believe it's this one right here. Okay, this is a rescaling. This is a covariance. This would be like making it standardized, which makes it a correlation. That's what that's telling us. But again, I wouldn't normally look at them. One thing I will compare and contrast. Actually, you had a question. Yes, Mike.
So is that a magnitude change or is that a directional change? What's the 3 and 4?
This is not even a change. This right here, this is expected. Yeah, so this is just telling you what the parameter would be if you estimated it.
Well, that is what it would be.
That's right.
So it's not going up or down.
Well, we have to remember it's 0 before. Depending on how we built this, it may not be 0 before, but that's telling you what the parameter should be. So between comparing and contrasting between the two, The residual covariances matrices will tell you where the problem is. The modification indices give you a lot more advice on how to fix it. Because this is saying add the covariance. Now, in our model, we haven't put in predictors yet. But when we do, anything that, that path model I showed you before, the big one, we had certain paths that were not estimated. All of those paths are going to be in here. And that will not only tell you, this will tell you where the problem lies, this tells you how to fix it. Right? This says, oh, you may have a big covariance matrix. You might say, oh, look, that standardized covariance between performance and usefulness is big. Now, how do I go fix that again? There's some quick ways that I'll show you, but how do I fix that with my model? It's not specific. It's saying that's where the problem lies. Whereas this is saying, yeah, add the covariance right there. Yeah. Yeah.
You continue on from their questioning.
Well, I was going to add a little bit that change is based off of your current model. So if you make a change, that can change everything else, yes?
Yes, that's right. And that's the other thing about this. These are 1 degree of freedom statistics. When you change one, technically speaking, the others aren't going to be valid anymore because this is a joint model. So you change one, even if it's one, like you remember that big path model, if we add one arrow and estimate one regression, all the other numbers are going to change because of it. So you add one and you look again, and you add one and you look again. And yes, you can automate this if you want to, but that just seems to take the brain out of it. Like it's just sort of a threshold, right? Did I answer your questions?
I have one more.
Yeah. Mm-hmm.
So, say we're doing a path model for the model for our project.
Yeah.
Many different parameters, many variances, things like that, and we don't have good fit. Would it literally be running this, and it would run it on all of our parameters, and it would line
Yeah.
literally everyone? Okay.
It will, but you can then search it and restrict it.
Okay.
Yes. I see the smile. Is that too much? It can be overwhelming. But here's what when I get to where we'll need that, I have some code that narrows it down. So basically, I will output either one type, right? Forget all the covariances. I really want to add a regression slope, or the opposite. Forget the regression slope. I only want to add covariances, or I would restrict it to the magnitude. Right? Only values bigger than 10. Only value. I think actually by default, I think R only does 10, but still. All right. Guess what? I'm up against break time. So let's take 10 minutes. Come back at 1:30, and I will resume the fun. All right. Welcome back. Should be recording in the middle. Double check. Yes. Hello, YouTube. Thanks for joining us. Those of you watching again, thanks for watching again. I hope this is better the second time. All right. Let's talk about the follow-up here. So on the next slide, I looked at this number. I said, this is big enough. I want to add this parameter. That turns out to be, boom, the model. We add the model. Actually, we've seen that before. Now, when we do that, we get the following estimate. The estimated parameter is 6.487. That was the value from our saturated model instead of 7.125. But apart from that, now things seem a bit better. We get better fit. So that is what modification does. So once again, global model fit indices tell you if you should even consider the model. If you really want to consider the model and they're not good, you dive into the local model fit indices, right? The residuals or the residual covariance matrix will tell you where the problems are. And I think modification indices tell you guides on how to fix it. Okay? Sound good?
So this is to say that this model is better than what we used before in comparison to the saturated model.
Right. Now, we're in that's exactly it. Yeah. Yeah. Well, we'll have another chance to see this as we go through the slides soon. So now, with all that in mind, let's add some predictors. All right? So this is now a multivariate regression. We're going to predict usefulness and performance with high school credit hours or high school courses. This is the number of high school courses in math someone's taken. and college credit hours. That's what CC happens to be. Now you'll note both of these is just a multiple regression, but we're going to estimate them both simultaneously. And because we have these two variables, you'll note I have to do weird things with all of my notation because it's no longer beta 1, because beta 1 would have been like your slope. Well, we have four slopes, right? So what do I do here? I have beta 0, that's always an intercept, but the intercept for which it's predicting I put in the superscript, right? So that's beta 0 for performance. This is beta 0 for usefulness. And when I'm saying beta 0, that means this is the intercept for performance, this is the intercept for usefulness. Right? So my superscript, I indicate which outcome that parameter is predicting. Okay? It looks complicated. I'm sorry about that. My notation is overly complicated. But then again, when I cut it down, I get into a spot where I'm like, it's beta 1. Which beta 1? Oh, the other beta 1. No, not. It's like you have to sort of narrow it down. All right. So either one of these you would interpret just as your typical multiple regression. Our only difference here is we're estimating them simultaneously in one maximum likelihood model, because that's the beginning part. This is a path model. It's just one where our variables are, well, let's just back up. Performance and usefulness, are they endogenous or exogenous variables? Remember that definition. Are performance and usefulness endogenous or exogenous variables? They are endogenous because they are being predicted. That's it. That is the distinction, right? So think of it this way. Endogenous is another way of saying that's an outcome somewhere in the model. Okay? Why do we use that term for it? I don't know exactly the derivation of endogenous, but I do know that what we're basically saying is we know these things vary, and we seek to describe why they vary. Okay? Now, HSL and CC, are those endogenous or exogenous variables? Exogenous, correct. That is telling us they vary, most likely vary. If they don't vary, they're just a constant. They're not going to do any good in our model, I can tell you that much. Right? But these vary, but we're not explaining or describing why they vary. Basically, for instance, in this case, you can think high school credit hours. Well, almost everyone going to high school. Now, I don't know what it was like. Well, I did go to high school in the early 90s. And there was very little variability about how many math courses you took in high school, right? You have to take at least 3, right? Some people took 4. So there's variability, but it's not big. But that is saying, yeah, it varies, but we're not describing why, right? College credit hours. There's a whole lot of variability there, right? It depends on where you started and what your major was, right? For me, I started in remedial algebra. I kid you not. That was where I started college in. College algebra. Didn't even count for credit toward my associate's degree. That's how much I failed at math in high school. So whenever I talk about this stuff and about math and stuff, I'm like, look, I've been at the bottom. Right? You should ask my family if they ever thought I would go to college, let alone teach college, right? Anyway, but yeah, these things vary quite a bit, but we're not seeking to describe it. We just want to know if variation in that explains variation in our endogenous variables. So that's what the definition of exogenous is. Okay? Now, it's pretty straightforward when you have a multivariate regression because the endogenous variables don't predict any other ones. They're predicted and that's it. When we get to path analysis, you might see performance or usefulness predicting performance. Right? That doesn't change that usefulness is endogenous or that performance is endogenous. It just means that there may be a relationship between usefulness and performance. Okay? So the distinction is always, if a variable shows up on the left-hand side of an equals, that's an endogenous variable or an outcome. If it's only on the right-hand side and doesn't exist on the left, that's exogenous. Okay? Great. So these are our 2 regressions. We have 2 error terms or residuals at the end of each line. So in any one univariate regression, we'd say that thing followed a normal distribution with some residual variance. But because we have 2 of them, we have a bivariate normal. or a two-dimensional normal distribution. I know we talked about that a couple weeks ago. The mean's always 0 for error, but it's the covariance matrix that shows up now, right? So sigma squared E colon performance. Now I couldn't put performance in the superscript there because I had a squared value there. So I put a colon down there again. That thing right there is the residual variance for the performance regression. Sigma squared E usefulness is the residual variance for the usefulness regression. But this is the unique thing about estimating them together. When we estimate them simultaneously, we're able to estimate a residual covariance, right? Which is how far they are off in the same direction, right? And that's one of the unique things about multivariate statistics. This is good and bad, right? We don't often put a lot of thought into it, but the joint estimation, why we have it there, does help in some ways stabilize the model estimates themselves. It's more of a Bayesian idea. I won't talk much about it right now. So this is the path diagram that we just have here, right? Again, trying to talk about the labels of path analysis because there's so much terminology in path analysis. We have our outcomes or endogenous variables for performance and usefulness. Each one of those, the black dashed arrows represents their residual variance. The dotted line with, these are two arrows. It's kind of hard to see with the curve of the dot there. This double-sided arrow, an undirected or bidirected path, as sometimes we call this, that is signifying the covariance between them. Okay. Then we have our predictors, high school math experience, college math experience. Each one of the red lines is there to show the regression slope, right, for all four. And now this is where I put different colors in. That's Illinois orange, Illinois blue. Big game this weekend against Indiana. It's like the first time I've talked about Illinois football since I think 2007. So that's where I got my PhD from. But yeah, anyway. These things are offset because these are exogenous, right? And depending on, some software programs don't even give you estimates for these. They don't even show up in the model output. They just exist, right? Some do. And we'll talk a little bit more about it in just a bit. But that's the variance for each. So now they're not residual, because to make a residual variance, you have to be predicted or endogenous. These are just variances. And there may be a covariance between them as well. Yes. No. That's just my drawing of it. Yeah. I don't know. I think left to right when I write things, and I probably put diagrams. But the irony is when you look at the equation, it's backwards. Yeah, exactly. Yeah, good observation. But yeah, I guess I do things left to right because I write in English. So, any question? No. All right. Excellent. All right. So we already talked about endogenous, exogenous. It's like I made these slides. Label those as well. Now, here's the fun thing about the exogenous variables. All right. Lavon will take those and make them part of the likelihood function. Now, you might think, what, how, why, what does that mean? What it's trying to do is that this is one of the weird distinctions about maximum likelihood. When we look at these models right here, what we're implying is that performance and usefulness follow this bivariate normal distribution. Lavon and many of these structural equation modeling packages, almost from tradition, based on knowledge we had when this really was invented or discovered, take these and say, that two-dimensional multivariate normal, let's make it 4. Right? Let's put both of those in the likelihood itself. The rationale for doing that, well, first of all, we didn't know any better back in the 70s, but now we know a little bit better. You do get a little bit missing data protection out of it that way. Because when variables are in a likelihood function, if somebody doesn't give you, let's say someone had missing data for high school math that had observed everywhere else, you can still keep them in the analysis. The problem with that, though, is that not all variables are multivariate normal. right? So our gender variable will not be. Now, that's why in my syntax, if you looked at the code to run Laban, I had an option called fixed x equals true, and that just means that it does not actually put them in the likelihood. It sort of substitutes what their value, the most likely estimates would be. It's a slight change. But by doing that, that means my syntax, I'm basically taking this and I'm going to force it to make me define these variables in syntax. And why I'm doing that is I want to pay attention to I want to know what goes under the hood. Some decisions make a difference, right? So I'm going to walk through this syntax that you see here. The top part is our regression. The bottom part is for putting the other variables in the model. This is overriding the fixed x, but just as a demonstration purpose. Okay. When we get to the real model, you'll see how to do this where we won't have to worry about this as much. But here, let's talk through the endogenous variables. When we want to use Laban to predict a variable, you like a regression, it looks very similar to the code that you would form in the LM formula in R, right? Where we have the outcome number, the name of the variable in your data set, perf, a single tilde, and then the name of each of the predictors separated by a plus, right? So here, you see performance and usefulness have different predictors. Whenever you have different variables, just because you name the predictors, those are the names in your data set, it will automatically estimate different parameters for each of these. They're not constraining them to be equal, okay? You can't, there are ways of making them constrained to be equal. I'm not going to show those yet. Actually, I had some in the code before, but we don't need to worry about that for the moment. Okay, I'm going overboard, right? This would most likely be enough to run the whole analysis and call it good, but I want to get you thinking about each of the parts of the model itself, right? So this is covering the regression slopes. If you put a 1 after a single tilde, that is covering the intercept, right? And I could have condensed this even more. I could have put this 1 on each of these lines with a plus afterwards as well, right? Then we have our residual variances, which is performance, the endogenous variable's name with a double tilde and its name again, right? The covariance of a variable with itself is its variance. So these will be residual variances because you're predicting both of these. And then we have a residual covariance, right? And so if you're thinking out loud, okay, what are the parts of that multivariate normal? We know we have a two-dimensional multivariate normal. This part covers the model for the means right here. This is the covariance in the off diagonal, and this is the diagonal of the variance, covariance matrix. Okay, that's where each of these line up to be. So I'm trying to make a connection between model parameters and where things show up because model fit depends on this, right? Then we get to the bottom part. Now this is me entering each of these into the likelihood, and then my rationale for entering these into the likelihood in this time is because I believe I have missing data on some of these. And when I put these into the likelihood, it will use all the observations. It'll just skip over a person who misses one of them. Skip over that one variable itself. Reason for that, so multivariate normal. If everybody gives you all 4 variables, there's like 4 dimensions to it. 4 by 4 covariance, right? If someone gives you 3, you can still use a multivariate normal. It just won't have 4 dimensions. It'll have 3. Right? So you can continue to use all the data that's in the data set. It's one of the good things about having these in the likelihood, but I just wanted to make it explicit so that we know what's going on. Here, we put in our exogenous variables with just their intercept. Right? When we don't predict them, the intercept becomes their mean. So that's the mean. We have the variances of each of those exogenous variables. These are not residual because we're not predicting them. And we have the covariance. And again, that's not residual. It's just happens to be. Yes.
Does this order make a difference?
The order does not make a difference. It makes a difference if you have a very big model. Because then you get into where did I put that parameter? That becomes a
Looking at, our HSLs, like at the top, and the bottom, and like, okay,
no. It gets translated into syntax where parameters show up and then are estimated. Okay. Other questions I should ask? By the way, how's my pace? Is this comfortable? Too fast? Too slow? I can't make everybody happy, but I don't want to like leave anybody behind, especially in the beginning right here. This is sort of, we will keep seeing this going through. All right, let's count our parameters. This is, by the way, not something I typically do, but when you have a big model, it does help. Why I say that is, if you look at your path diagram, and I have 16 slopes in estimating, you want to make sure that those are in the model. Syntax, once you start having lots of variables, becomes harder and harder to make sure it's perfect, right? But let's count, right? We know for this, way I built the syntax, we'll have these 4 variables, they'll all be in a multivariate normal likelihood function. That means in the multivariate normal, the saturated model will have 4 means, 1 for each of those variables, 4 variances, 1 for each of those variables, and then for every pair of the variables, 6 covariances, right? So that's 4 choose 2 every pair, right? Our model turns out to have 4 intercepts, 4 slopes, 2 residual variances, right, between the endogenous for each of the endogenous variables, 1 residual covariance for the endogenous, 2 exogenous variances, and 1 exogenous covariance. It has 14 parameters. Guess what? We have a saturated model. Model fit is perfect. You don't need to worry about residual covariances. You don't need to worry about modification indices. I wouldn't even report model fit statistics because they're sort of ridiculous. Although I've said that to people before, they haven't reported them, only to have editors and reviewers say, "Where's the model fit statistics?" The model fits perfectly. 0 degrees of freedom. It's equivalent to saturated. Okay, so let's put numbers to this. When we estimate it, you'll see the numbers. All right. I have a number for each, and then I have its standard error. This comes straight from the Levon output from the model itself. But you can see each of these values right here. Right? The slope for high school math on performance is 0.984. That means for every 1 more class of high school math, you would get almost 1 point more on the performance test. I think it was an 18-item performance test. For college math experience, that slope is 0.079. Now it's different because college is in credit hours, high school is in classes, right? So this is for every credit hour. Now, how many, you teach college math, Michael? What are the credit hours of your classes?
Well, I'm a course where we have 4 components, next to it, normally like 3 or 4.
3 or 4?
Occasionally,
Okay, so this is what I'm saying. Like math courses in college, a course would be like 5 of these potentially, or 4 of those, depending on the math course you're taking, right? So really, it's hard to compare, right? But also, this is on a different metric because, I mean, well, both of those are together there. But basically, as the number of hours of your math experience go up in college, this does say that you have more performance, right? About a little under 1/10 of a point per credit hour in college for math. Similarly with mathematics usefulness. Now, this is a weird thing. This is a number correct out of how many on a scale. So these are more now Likert type item values. Those still have the same. You'll have, yes, it's an added, yeah, yeah, it's how you feel about how useful math is. And I think it was on a Likert scale, so I don't exactly know. But why I'm saying that is for every 1 more course in high school, you would rate an item, or your total score for usefulness would go up by 1.466 points. And same with college math. Now, you'll note here, this one's likely to be not significant, right? Because the standard error is 0.015, so it's probably not going to be. Then we have the same values. So our residual, we have our variances and covariances for the exogenous, and we have the residual covariances here. Let's keep going. We talked a little bit about standardized units the last time, correct? So let's talk a little bit more about that. Right? The scale, we just saw, these are the unstandardized values right here, right? Meaning when I described this, I said 1 course in high school, for a 1 course increase in high school, performance goes up by 1 point almost, right? Yes, question. Good question. Do I have that? Give me a second and I can run it for you. But it is going to look very similar to, just a moment here. There we go. Yeah, so the output will look like this. All of our model fit should be perfect. Sorry, this is a little too small. Can you see that better? That better? Sorry about that. So our model test user model, that just tells us we're saturated. We have no degrees of freedom. Why we have a number in our baseline model is because that's nothing to do with us. That's comparing saturated to independence. And we know there are 6 correlations or covariances, and that's why there's 6 degrees of freedom there. Okay. Our CFI and TLI are exactly 1, which should be where they're at for really good fit. The RMSEA is exactly 0 or NA even. Don't report NA, put 0. And then standardized root mean squared residual is 0, but where I got the coefficients from are here. So under the regression section, it outlines your outcome or your endogenous variable, and then it has each of the predictors for that in each. And then our covariances. And here you'll note it does not make a distinction for covariances between endogenous or exogenous with the exception of that little dot right there. The standard error, that's right. Here, why I put the standard error is that the standard error tells you how much, sort of on the same metric. A p-value tells you if it's bigger than 0. This tells you how much certainty you have, right? So if you wanted to quickly do a confidence interval around it, the quick and dirty plus or minus 2 times that would give you a confidence interval around it, right? So that's where I put that there. But again, there's no, you can do, yeah, if you like the p-value, you're not alone. So it's just neat the way I put it on here. But good question.
Just to add a little context, they also keep the standard error, but they'll put like little stars. And the star are the ones that are significant.
Yep.
So
That's
when you're saying insignificant, you are saying that the confidence interval includes 0 on college bound to math.
that's it. Yep. That's where I was looking at. I should have put the stars there. Yeah, that's right. No, that's good. And then let's go just real quick on the other part of the output. Performance and usefulness. You know that this is a covariance, but there's a dot in front of each. That's your indicator. Those are endogenous variables, right? So this is an endogenous or residual. So when you see that dot, look down here under variance also, you wouldn't call these variances, you'd call them residual variances, right? You wouldn't call this a covariance, you would call it a residual covariance. Right? It's a subtle distinction, but you understand the difference, right? A residual covariance is what's left over after we've done the predicting. A covariance is just what it is between 2 variables, right? Intercepts are also listed here. Again, you could denote, we don't call those residual intercepts though, that's just the dot shows up there to tell you which ones are endogenous versus exogenous. I don't even know why they have that for intercept. There's no distinction between either. Apart from, I will say this, actually there is a distinction. These are conditional means, right? How we read this is 8.264 is the mean of performance, but with that dot it says when HSL is 0 and CC is 0, right? So that's probably why. So what we're saying is if you're a person who never took math in high school and never took math in college, you're still going to get eight of the questions right on this math test. That doesn't seem reasonable, but whatever. It's just by going to the store and using everyday math. Or maybe what you picked up before high school. Then you have the HSL and CC. What we would say about these is this is just the mean, right? This is the average number of high school courses, which is weird because 4.9, that doesn't seem reasonable. And then the average number of college credit hours, which is 10. And then similarly, we have our residual variances and then our non-residual variances below. Thank you for asking about that. I should have had that up earlier. Other thing I want to note on the path diagram is we don't have a spot for intercepts anywhere. And so if you are talking to a guy like me and you're like, let me show you my model, and you show me this diagram, I'd be like, not a model because I don't have all the parameters. But to everybody else in the world, this is a model, okay? But just know that all of the parameters that show up, this is a more of a conceptual idea, right? It's like the mathematical way I'd say this is a picture is not this picture is not isomorphic with the model you're running, meaning that there's no one-to-one correspondence between the symbols on the picture and all of the parameters because we're missing intercepts, for instance. We got most of the things there, but why intercepts? Why do we just forget the intercepts, right? That's how it works. There. You people have put other ways to do this, not so much in path diagrams, but when we get into latent variable models, factor analysis, item response theory, a lot of times they'll have a latent variable mean, and they will denote that with a triangle. I kid you not. So in this diagram, we have rectangles, we have arrows with one arrow point, we have arrows with two arrow points, we'll have triangles. I want a rhombus. That'd be great. And the line that Lisa likes to quote.
When you're making your diagrams, you're mapping other logistical things.
Yeah.
That's what
The way I like to joke about this is circle plus square does not equal triangle. That's not how it works, but it does convey a lot of information quickly, just not all of it. So that's the one caution and caveat. And then the other thing I want to talk about was the standardized coefficients. I mentioned before a little bit about standardized. I'm going to bring that concept back a little bit, right? Our coefficients that I read to you from the diagram, the unstandardized coefficients, are given in units of y per units of x. Right? This is how a regression works, right? For every 1 hour or one more class of high school, you get one more point correct on the test. Now, the key in listening to that is 1 more hour, 1 more point. Units of x is 1 more hour, units of y is 1 more point, right? Where the distinction came in was, oh, wait, this is 1 more class, this is 1 more credit hour. There are different scales, right? So to try to make this more understandable, we rescale them, right? We take the units off, is another way of putting it. It's my stoichiometry example from the last time.
Yes.
Which is where I always feel bad because I failed chemistry in high school as well. And it's probably because of that, right? So I'm going to say that this is a loosely following chemistry example that has probably many holes in it and I probably shouldn't use, but I'll learn. Here, what we do to do that is we take the regression coefficient and very similar to stoichiometry, if we know we have units of y and over units of x, and we want to remove them, we can divide by the standard deviation of y and multiply by the standard deviation of x, and we basically standardize them. We remove the units. And so when we do that, what we can see is the standardized coefficient predicting performance from math, from high school math, is 0.984, and the standardized coefficient from college math is 0.079. And now I noted that those are the standardized coefficients in this diagram. So if I go back to the unstandardized, wait a minute, what am I talking about here? I have a typo there too? Oh my goodness. Oh wait, no, this is just describing them. These are unstandardized. Let me go back and say this again. Read my slide wrong. God, template. All right, here we go. These are the unstandardized, saying for every 1 high school course, you get 1 point more in math, but high school had a standard deviation of 1.31, and for every college credit hour, you got 0.079 more points right on the math test, but the standard deviation of that was 0.588. Right? So if we go and standardize these coefficients, We can do that, by the way, by adding the standardized equals true to the Lavon summary statement in R, the summary syntax value right here. And when we do that, we can get this column that says std.all. That's when we'll be looking. There's another column that says std.lv. That is when you have a latent variable. That's a different type of standardization. It standardizes based on the latent variable, but not on y. The reason why why we need that, we'll get to in a few weeks. For us in path analysis, std.all is what we'd want right here. And that shows you sort of the relative strengths of each of these coefficients on a standard basis, right? And how we interpret those is the following, right? For every one standard deviation increase in high school math, performance will go up 0.438 standard deviations, right? And for every one standard deviation increase in college math, performance goes up 0.157 standard deviations. Okay? So now we can say what the relative strength is that high school math seemed to have a bit stronger regression weight than college math. But that also gets into dangerous territory when we evaluate strength of regression weights because they're conditional on what's in the model itself, right? We put a different variable in, it's related, that might change things as well.
When we talk about this narrative, we use the capital beta symbol, right?
Capital beta?
Yeah,
I don't know. I think it may be B.
Psychology writing, you have to be very specific about what you use because if beta is only a standardized, but since I've been in education, they just use whatever they want.
Yeah, and I work, the places when I do this type of help with other people, it's been everything. It may not be any beta at all. It might just be the slope was or something along those lines, right? Yeah. I'm the wrong guy to ask to chill out. I'm a pretty high strung individual usually. I know it doesn't seem like that. You only see me freak out just 2 or 3 times during class. But yeah. So this is how you get this. These actually, there's only 2 standardized. They don't have any more here. But well, so it's interesting. Really, to get a standardized solution, we are multiplying beta by the standard deviation of x and dividing by the standard deviation of y. But depending on what the beta represents, that may not be very logical, right? So if you have a dummy coded variable, right, where the mean and the standard deviation are yoked, people used to offset that and say, well, don't standardize by the dummy variable because it's like, what's a standard deviation increase? It's a 0 or a 1, the end, right? That's where that had shown up before. The latent variable is another special case, and we'll get to that in just a bit. That's special mainly because you get to pick how you handle the variance of the latent variable because it doesn't exist. You don't worry about that today. We're path analysis today, okay? And we interpreted this already. I think I need to talk about that. Oh, one last thing I do want to talk about though. The standardized coefficient here under the covariances, these are really interpretable. A standardized covariance is a correlation. So this is super interpretable, meaning the correlation or the residual correlation between performance and usefulness is 0.072. Right? The correlation between high school and college math is 0.167. And what you'll see, if we wanted to say, is this a significant residual covariance? It's not significant, right? So it's like 0. But what does that mean? It doesn't really mean a whole lot for us here in what we're doing. We're basically off the same amount for both randomly, not in the same direction. Okay. Okay, the other thing we can get is R squared. We have 2 outcomes. We should have 2 R squareds. And it turns out, using the Lavon command, we can get the output. This command right here. And what this tells us is we explain, oh, you can't see that, can you? Is that better? We explain 24% of the variance in performance with this model, but we only explain 2.4% of the variance in perceived usefulness of mathematics. Okay? So, multivariate regression. Questions? Basically, two regressions. So, the thought was you know about regression coming into this course. I thought, all right, let's make it two. Because going from 1 to 2 introduces maximum likelihood, introduces the need to describe model fit, introduces a lot. And the only thing I can just summarize it as path analyses, multivariate regressions, these are multivariate models, meaning something with a joint multivariate distribution or more than one outcome, right? I always remember I was a kid, when I was a kid, I was in high school, I remember they had I'm sort of a aviation nut. I don't know why. I've never flown a plane, but I like planes a lot. And I went to some like aviation day, in Sacramento, where I got in a small plane. I remember it was my first time in a small plane, single engine, taking off. And as we're taking off, the pilot's like, "Where's that other airplane?" I'm like, "Oh my God, what's?" And he's looking up and he's looking down and he's looking wherever. And it's like, "Oh, this is exactly this is the perfect analogy for what we're doing here. Is that when you're driving your car, you've got two directions to look for where traffic is, right? You don't look up, you don't look down, because if you're up or down, there's going to be bad things happening anyway, right? If you're going to get hit by something like that, you're looking left, you're looking right, right? When you get in an airplane, now all of a sudden you've got other dimensions that you now have to look at, right? You got a third dimension, up, down, all sorts of things. So I look at the idea of multivariate models as going from like the car to the plane, right? We just have to look in more places for how to make them work. That is model fit, that's remedying model fit, and that's understanding a bit of maximum likelihood. So that was the purpose in having this here in this lecture. What we're about to get into in the rest of the lecture, I'm not going to focus on this next unit is what we call identification. That's how do we know the path model is estimable. I'll go through that quickly. But the last part of this is actually doing it. And I really want to get to doing the path model, right? So this is all the nuts and bolts getting you set up. Let me give you the identification next. Actually, before I move to identification, let me stop and ask, do you have questions on anything I've shown? Welcome any questions. In the absence of questions, I will keep it quiet. Keep moving. All right, identification of path models. I bet you're saying, I look at a picture, if there's rectangles and circles and triangles and arrows, it's a path model, and if it's not a path model. But that's not what identification means from a statistical point of view. Identification is the statistical concept that your model results mean something. Put another way, there's one set of numbers that solves the estimation process for your model, right? Why that's important is, now you've never probably worked with models before that are unidentified. But what that really means is an unidentified model is there could be a whole set of numbers that are equally possible that give you the same result. Same predictions, same likelihood, same so forth. So identification can be a very important part. We are going to keep it basic here. This is if you are studying path analysis, like to be a methodologist, you will have to do a lot more on this, but I'm just going to keep it simple for this, okay? Simplified, because that gets us most of the way. So we're going to do this, look at it in two ways. There's a global and a local identification. Global is, can I estimate the whole thing? Local is, if I just took one section of it, would it be estimable by itself? Okay? All right. And so, technically speaking, if you can show that the model is, get that out of the way. I almost spilled, but I had a lid. That's all right. Or maybe I'll just open that later. Path models are done. Celebration. That's what I really should do in like at the end, like in sports, when people win a championship in the locker room, they're spraying I'm gonna get Sprite and spray you guys. Woo! My last lecture in this class is my last lecture at Iowa. I might be doing that. Like, oh yeah. Better you could do that and spray me on your everyone. That's it. That's it for your presentations. Maybe I'll let you bring in water balloons also, or champagne. Maybe not champagne. Oh, that's my last lecture here. I mean, if I'm going to go out in style, right? Good point. That's right. We get the lawn, we get the bar. I mean, one or the other. All right. So if you have global identification and local identification, your model will be identified. But let's just keep it together. There's something I don't know why somebody came up with the name the T rule. The T rule isn't the T rule. It's just count already. All right. Basically, the idea is you need in your model to have fewer parameters estimated than there would be in the saturated model. Right. And so when I laid out the number of parameters in the saturated model in our previous example, and there were 14, and we saw that our model had 14, that means based on global identification, it was globally identified. Hooray! T rule. I don't know where T comes. I can't even T. Maybe the T stands for total. Just add it up. Count it. Count it is really what you got to do, right? That's that. Now I will say, if you have you want math on this, because I'm the guy that had math in his syllabus, right? I had equations in my syllabus. And you know what's funny about that? I put them in my syllabus. I told Lisa that, and she's like, "You put equations in your syllabus?" I'm like, "Yeah," and like, of course, that's what I do. And she's like, "No one puts equations in their syllabus." Anyway, I'm proud of that now. Like, made me feel unique. If P is the number of endogenous variables and Q is the number of of exogenous variables, we sum those together to the number S, and S times S plus 1 over 2 is the total, right? So going back to our example from before, we had 4 total endogenous and exogenous variables. 4 times 3 is 12, divided by 2 is 6. That's the number of unique elements in the covariance matrix. And actually, I'm oversimplifying this even more. It's the covariance matrix is really the thing that we really need to worry about. There we go. All right, let's go here. There are different distinctions of identification. These do follow with us to structural equation modeling or factor analysis. A just identified model means you have exactly the number of covariances in your saturated model as you have parameters for those in your specific model. Over identified, so just identified, if you look at your likelihood ratio test at the top of model fit, if you look at this thing right here, model test user model, if degrees of freedom is 0, it is just identified. Okay? If degrees of freedom are positive, it is over identified. Another way of putting it is the number of covariances in your saturated model exceeds the number of model parameters for those. And then finally, under identified is not the spot you want to be in. Lavon will not even run. In fact, you will not get negative degrees of freedom. Under identified is when you have too many model parameters and too few covariances in your saturated model. So this is not good.
This, can you remind me what we have to look at the test model test user for the under it? It won't even run.
It will not. If it runs, there'll be a lot of error and warning messages. I don't think it would even put an NA here because I'm guessing they have a catch. The degrees of freedom should never be negative. I've seen degrees of freedom have non-integer values, decimal values before. You see that in mixed models like Satterthwaite or Kinward-Wadger degrees of freedom when you're doing a degree of freedom correction in a multivariate model, but it should never ever be negative. So under identifies that. But these terms are going to come back to us in factor analysis too. And where they actually come from, if you remember math class, remember systems of equations? I know. Oh, wait, no. I'm sorry. I'm just ruining everybody's day. Wait till I pull out the Cholesky decomposition. That's not coming in this class, don't worry. In system of equations, you have a number of equations and you have a number of unknowns, right? And to solve a system of equations, it needs to either have the same number of equations as you have unknowns, which would be just identified, or you need to have more equations than you have unknowns, which would be over-identified. In that latter case, you typically would see that in a matrix or linear algebra class. Many of you wouldn't normally see that. But that system of equations idea, which I think you got into in Algebra 2 type concept initially, maybe wrong about that, maybe just be algebra. Yeah, that's where these terms come from. And if you remember systems of equations where you had to do some substitution, remember what I'm talking about? I know. Here, let me. Do I want to do this? I don't know. Forget it. If we were like, solve for y in one, go plug it into the next one. Right. You know what I'm talking about with that, right? Actually, I will do this. Of course, I killed QuickTime, so I have to do this one more time. Oh, come on, Templin. Why I'm saying this? So, a system of equation might be x equals y plus 2, and then y equals 1, or x minus 1, or something along those lines. And you would have to, oh, look, insert graph. Oh, Apple Intelligence has gotten, I wouldn't say intelligent, but that's, better. You have to go and solve one, plug it into the other, that type of work. That actually is what's happening. We can actually trace what's happening in the covariances that way. Like what you would end up doing for these models is that these things are covariances and these things are model parameters, and there's a function of that, and we can go figure that out, what that is. And we're going to see a little bit more of that when we get to factor analysis, but that's why those terms show up, okay? Link that together. And so, yes, when I was in Algebra 2, failed Algebra 2, got a D in pre-calculus. But when I was in Algebra 2, I thought, I am never going to use this. And boy, that's the truth, right? Anyway. All right. So, once again, just over and under, and we are just about on break. So, just meaning 0 degrees of freedom, or equivalent number of saturated model covariances to model parameters for them. Over is saturated model has more than what we have, and then under is danger. All right, let's take a break. 10 minutes. Enjoy the everything that Schaefer Hall has to offer, and we'll be back. And I'll do hopefully get into the fun stuff after this. All right, one last bit about identification, and we'll get to practical. So to identify a model, you need to look global and local. Global is count the parameters, right? Local is take a look and see. This is my very trimmed down version of this, okay? So if you go to David Kaplan or someone who probably knows a lot better than I do, they'll be like, wait, it's more nuanced than that. Yes, it is. Acknowledge it. But here's the big thing. We can define two types of path models, recursive and non-recursive, right? A recursive path model is one where there's no feedback loop. What I mean by that is if you trace from start to finish, you can't get back to where you were if you follow the arrows with any of them. And where the hard part is does a bidirectional arrow indicate a recursive? And what I'm talking about here is forget anything bidirectional, just with the straight arrow paths, the direct effects, okay? Right there. So our example, the bivariate, multivariate regression that we had here with 2 is recursive. The big model that we started with class with is recursive. Those are estimable. That's identified. That's good. Where things get weird is if you have a non-recursive path model. That's where a feedback loop is present, right? There are all sorts of these in the world. You may encounter some of them, but typically what people have to do to put numbers to them is come up with really weird estimation methods. Partial least squares, things that show up that have weird words to them. These are really hard to do. This is a recursive model, right? Why do I say that? We start here, follow the arrow to college math experience. It goes to self-efficacy. There's no way to get back. Similarly, start here, no way to get back. Look at this variable, no way to get back to it. That is a recursive model. A non-recursive model might look like this. High school math experience predicts college math experience. College math experience predicts math self-efficacy, but math self-efficacy predicts college math experience. Now think for a moment here why this is not identified. We don't need math. We can think about it conceptually. I know we actually always need math. That's probably that's me trying to be a normal person. I realize now that I'm old enough, this is just who I am. I'm not normal. Okay. But maybe more Bernoulli. Oh, sorry, I said this. This right here, conceptually, think of it this way. This model is saying the more college math experience you have, the better your self-efficacy is. And better your self-efficacy is, the more college math experience you have. But the data we're going to collect for this, if it's like what we have here, it's cross-sectional. It's one snapshot. So how could you disentangle that process from one snapshot? Because all you have is one measure of college math for a person and one measure of math self-efficacy for a person. Yes?
Is there actually a time where there's a both and recursive and not recursive where there's a feedback loop, but then also
So if you have any feedback loop, it becomes non-recursive. And this is only again with the direct effects. These things right here. When you have the residuals, that one is treated a little bit differently. Now I know in the book, I think I had you read, it sort of said, okay, those technically are a loop. That's an estimable loop. Because that's actually a part of the covariance matrix that's easy to identify.
Math person did not come up with those names.
No, probably not.
Recursive, not recursive. I'm assuming that's what you're saying.
I can never keep them straight either. Like I want this to be non-recursive because I see the recursive and the recurve. Yeah, no, I have to tell you, like if you stop me on the street, literally my car is parked 3 blocks that way. If you stop me 2 blocks down the street, I'll tell you this wrong. Okay? It happens. Feedback loop or no feedback loop. Cool? So the two things you need to make sure of for your path model to work on a very basic sense. Number of parameters, no feedback loops. Right? That work? Okay. Let's put it together then. Finally. Here are the steps. And I had to when I made this slide, I was like, oh my God, I'm going to run out of space. So I had to like, this is a non-recursive path model. Sometimes that's what we should call it. Does your path model look like a flow chart? Because then it's non-recursive. I guess flowcharts can all be recursive. You know what? Maybe that's it. The next time you see a flowchart in someone's class or in your life, label it recursive or non-recursive. There you go. Oh, sorry, man. That's just what my path analysis teacher decided to tell me. All right, here's how it works. The process. You formulate a hypothesized model. That's why you start the study in the first place, right? You check to see if the model's identified. If it's not, you can kick your computer, but really that's on you. The computer didn't do that, right? So there, if it's identified, you collect your data and you estimate your model. Hooray! Did the algorithm converge? Well, most of the time for these models, it's pretty well behaved. It will usually converge, but if it doesn't, start back again and reformulate the model. It's usually a problem with the model. Either a hidden identification problem is usually what you see when the model doesn't converge. The alternative is if you have two variables that are perfectly correlated. And where you normally see that would be variable A plus variable B. So you put variable A in, you put variable B in, and you put their sum in. All three of those are going to cause what we call empirical under-identification. Now, a question.
So when it doesn't converge,
Mm-hmm.
does the computer understand it does not converge? It stops after an amount of time.
Yes.
Or you follow.
Yeah, Levon will stop. M plus will stop. Both will give you numbers, though. You have to go to the top of the output to see model did not converge, because both will tell you values where it stopped at. Those are not usable. The model doesn't converge. Like when you use maximum likelihood, if it didn't converge, that means you didn't hit the maximum. And why we call it maximum likelihood is if you don't hit the maximum, that's again this likelihood function, it's garbage. It's not, I wouldn't say garbage. It doesn't have the properties statistically that we trust about results. So convergence is important. Now, you can have convergence, but you can have what I call unstable estimates. Those are ones where you look at the standard error and it's ridiculously big compared to the point estimate. Now, I don't mean like magnitude of 10. I mean like a standard error of 2 million, right? Scientific notation standard error with a point estimate of 1. Because that also indicates a form of non-convergence potentially, right? So if it doesn't, you got to kick the computer. Now, then, once you get to that part, does it have good model fit? And this is normally I usually take these parts for granted right here, because most of the time it behaves. It's this loop right here that's the problem, right? If you don't have good model fit, kick the computer, but you got to reformulate the hypothesized model. That's where the local model fit and modification indices, residual covariance matrix make the difference. And then finally, once it has good model fit, then interpret the results. Okay. So what you didn't see in linear regression was kicking the computer, right? That thing worked almost all the time. Now, you couldn't put in data that were dependent. You couldn't have the A plus B and then there's some in the model that would break it. But for the most part, did any of you ever run into problems running a linear regression? Probably not, right? That's yet another difference in this type of approach. But that being said, I've done a lot of really complicated models before. These ones will work most of the time. If they don't work, it's usually check that correlation matrix in your data for the variables. Make sure that's not a 1 or a -1 for a correlation. And then check the number of parameters you have, or there's a feedback loop. Okay, so our destination is this. This is the original model that I led the class with. Do you need me to go over it again? Okay. So let's talk about the questions. How many variables are in our model? 7. Gender, HSL, high school, college math, math self-concept, math self-efficacy, performance, and usefulness. There are 6 endogenous variables. That means 6 rectangles where one arrow terminates. Right? So 1, 2, 3, 4, 5, 6. We have 1 exogenous variable. Okay? Cool? All right. Is the model recursive or non-recursive? Well, if you start with each variable, you trace your way through, you can't come back. And on this one, there's no double bidirectional arrows. So there's really no way to come back on this one. Okay. So that means local identification is true. How about the number of parameters? Well, let's do the T rule. There are 28 covariances and variances in our all variable covariance matrix. How many model parameters do we estimate? We have 12 direct paths. That's 12 of those slopes. 6 residual variances. 1 variance in the exogenous variable. That means we have 19 model parameters for the covariance, right? So really the thing we're looking at, these are the variables that impact the T rule. Your direct effects, the regression slopes, the residual variances, and the exogenous variable variance covariance. So there's 19. That's less than 28. We're good, right? We need this to be less than the saturated model. Now you'll note there are 6 intercepts. Well, I'm not even talking about those. Those are on the mean side. So that is going to be identified. In fact, it's really hard to unidentify the mean side because if you put a 0 there, it becomes 0. It's still estimable. And if you put another constant there, it gets smushed into the mean and estimated as 1. So we don't really look at intercepts for identification. There are probably some models where we haven't. But what that means is our model is over-identified. In fact, not only over-identified, how many degrees of freedom do you think will be in that top test comparing our model with the saturated model? Yeah. Right? The saturated model has 28 terms, and we have 9 fewer. Right? We have 19. And that degrees of freedom is literally the difference between how many parameters there are in the saturated model and how many there are in our model. Now, I will say, those degrees of freedom do include intercepts, but the saturated model has 6, or 7 if you include the exogenous variable mean, and ours has 7. So it's saturated as well too. There will be no addition or subtraction of degrees of freedom from the intercept or mean side. Okay? So we have identification. First step in the flow chart. Great. This is the model in equation form. What I did this is just literally to reinforce we have 6 linear regressions. And unlike the multivariate regression model, though, here you will note that some endogenous variables are also predictors. Right? So that means estimating this with a series of separate, you could estimate this with a series of separate regressions, but it fits even more nicely into this framework for path analysis if we put it all in one spot here.
So that's essentially a version
It's okay.
of an equation.
Yep, that's right.
It's on there, it's right there.
Yep.
This is essentially the equation that will get us to our little numbers on our map.
That's exactly it. This is what that schematic diagram is implying all at once. Good point. So let's take a look at the Lavon syntax. And instead of squinting at the screen, I'll put the syntax over here. And I will move the regressions over here. I'm doing this to sort of line up each of the models. So here, I work backwards. I started with performance, right? But we have our endogenous variable equations. What we should see here is each one of these predictors on performance separated by a plus. So we've got HSL, MSC, and MSE. And you can just go down each and build that. I think in equations, so I use the equations for this, but you can think in the path diagram, it would work the same, right? Now again, I'm being ridiculously verbose in the syntax here, right? I don't necessarily need to put the ones here. Depending on how I estimate the estimation function in Lavon, if I use the SEM function, it'll put them in for me. Some Lavon functions won't, but don't worry about that for right now. So we have our intercepts, we have our residual variances as well too. Now you'll note, I don't have any residual covariances. You might think, do I need those? Don't worry about it right now. We will actually find out if we need a residual covariance based on our model fit exercise coming up. So this is all the endogenous variables, but what's not noted here are so this is the residual covariances. Sorry, these are the residuals. And I'm, again, being ridiculously verbose. I'm just putting too much in here. But I set all these, that when I put a number and a star in front of the variable name, that fixes a parameter to 0. Now, in residual covariances in Lavon, by default, they're set to 0 anyway. You have to actually specify them to estimate them. And the same thing happens in M+. But here, this is just reminding you, they could be part of the model, but I'm setting them all to 0. Okay? You don't have to do it that way, but I'm just doing it to give you all the details right now.
So if you wanted to just list everything, could you put zeros for the ones you want out and ones for the ones you want in?
Yeah, for the ones I want in, I would just take out the 0 and the star, and it would estimate it. Yep. And actually, I'm foreshadowing a bit here for.
Oh, sorry.
No. We're gonna need them. Then we have our exogenous variable. It says variables here, but that is 1. And I will note this gender variable is dummy coded. This, by putting this into the likelihood, it's going to treat it as multivariate normal. That's not ideal. But to fix that, the remedy for it is ridiculous in some ways, now, especially in Lavon. In M+, you can fix it a little bit better. What ends up happening is we're treating this as multivariate normal when it shouldn't be, which means we have one more parameter for it than we need. They're redundant. But it doesn't tend to bias results, so you see it happen quite a bit. The fixed in a maximum likelihood sense is you need a Bernoulli likelihood here, and the joint distribution gets weird, and model fit gets weird. And so what ends up happening is the structural equation modeling software says, forget it. Lavon will not estimate Bernoulli variables with straight maximum likelihood. It uses something called limited information, which we'll talk about when we get to item response theory. So that wouldn't work. M plus will, but then you won't see any model fit. And then the other option for all this is Bayes, because Bayes you can do anything in, right, Erica? That's right. For those of you who are listening at home, the answer is yes. She's shaking her head no. No, I don't think you heard me. I'm just kidding. The Bayesian system itself works very differently in terms of model fit and likelihood-based ideas. But that is our Lavon syntax. Any questions on Lavon syntax before I flip to how we get this to work? Whoops, where it goes.
So
Yes.
we got a bidirectional error. We could not do this.
Well, no, a bidirectional arrow we can. So let's talk about if you have a bidirectional. So what's a bidirectional arrow? When we have a bidirectional, this is the problem with the circle plus square equals triangle here. Because a bidirectional arrow here does not really indicate what's happening as a parameter. We use that bidirectional arrow. Oh my goodness, where's my cursor? We use it to indicate covariance, right? And covariances are perfectly estimable, right? The one thing that there may be redundancy in it, but we couldn't do it here. So what we're going to find out is the covariance of the saturated model, what the slopes here do, right? For instance, let's take the covariance between performance and HSL. Because we have a slope for HSL predicting performance, it is going to try to use that covariance between the two to estimate that slope. But if we all of a sudden come down to HSL and performance there, now we have two parameters trying to do the job of one. That's not okay. However, if, and this is a big, let's try a different way. Performance and usefulness, right? There's no arrows between them. Same thing would happen. If I put usefulness here and usefulness there, two parameters are trying to describe that covariance. That's not going to work. Now we have an infinite set of solutions for it. However, if I want to achieve the same goal, I come down here and I free this covariance, I estimate the parameter for it. And so that's the mathematical distinction. Where the path model itself, the bidirectional arrow, looks like a loop, it's really trying to tell us there's a covariance estimated there. And a covariance is perfectly estimable so long as it's the only thing. And I'm going to go one step further. This is probably too much information, but it's relevant. Performance and usefulness, there's a covariance between them, right? We can sort of solve that problem of the covariance by putting one slope in, one, either here, put performance on this line, or usefulness on the performance line. Or we could solve it with the covariance down here, but we can't solve it with both, right? We can only have one, pick one, here, here, or here. Performance as a slope, usefulness as a slope, or covariance between the two. They're equivalent in fit. How about that? It depends on what you want to do to describe. So when we fit our first model just a few minutes ago, the multivariate regression, it was equivalent to saturated. But no one asks, why didn't we just look at the saturated and call that good? And that's because the covariance there is in units of x times units of y, which doesn't get described very well. So we converted that to units of y per units of x. That's called a regression slope, right? So depending on how you want to describe what's happening, you may pick one or the other. But they are mathematically equivalent models. There you have it. It's weird, right? Sounds like it's an arbitrary distinction, but there's not, you go back to the slides from an hour ago when I was looking at the multivariate regression. I could have taken that covariance and taken the standard deviations or the square root of the diagonal and formed a regression coefficient from it. I need those numbers, but all those numbers are present, so I could do that. That makes sense? Too much information. We'll get into this in just a bit. All right, so we have identification, we have code, we estimate the model, and it said Levon ended normally after 68 iterations. That's where I need to open up the bottle of, here it comes. Oh, it's good. It's because I already done some damage to it. All right. It worked. So now we got to check for some abnormally large standard errors. Now, again, how would you know it's abnormally large? I'm just going to skip on the way down here. But abnormally large, again, I have a 19 for a standard error, but look at the point estimate. It's 243, right? So the scale of this is commensurate. I'm thinking the normal, like, go put two slopes in. Put the slope for usefulness on performance, put the slope for performance on usefulness, and this thing will be like 10E6, and that estimate will be like 2, right? That's the difference. Like 100,000 standard error with an estimate of 2 usually indicates a problem. All right, so it estimated, it converged, and we have stable standard errors. Next step on the flow chart is check model fit. We haven't had to kick the computer yet, and I don't want to kick. This is like my favorite machine ever. My M4 MacBook Pro. Don't kick it. No, okay, but that didn't do the problem here. I'm not going to kick my computer. All right, let's go through our model fit statistics, but just an output. I didn't run the model. Come on, Jonathan. I'm like, this is not saturated. We just said there should be 9 degrees of freedom. I did get some warning messages though, right? Some observed variances are a factor of 1,000 times larger than others. Well, yeah. Can you guess which ones? If I just go back here, I'm going to point to the culprit. The maximum variance you can have in a Bernoulli variable, right, is when a Bernoulli variable, the variance is the mean times 1 minus the mean. So in that case, at 0.5, if we had exactly 50% of the people who were identified as male versus female, maximum variance would be 0.25. But we have other variables on a scale that had variances in the 200s, right? And that's what's telling us. You've got a variance 1,000 times larger. Yeah, because we got a point, something smaller than 0.25 and something bigger than 250. That triggers the warning. This looks bad. It looks like, it says the bottom model is not identified, but that's more of an indicator of us throwing this in the likelihood as well, too. That does tend to happen with it. But it did converge. So if you see those warnings, it is good to look at your data, but convergence happened, and because the model fit, the standard errors were fairly well behaved. That's another way I like to put it. And I don't describe my child that way, as well behaved or otherwise. I don't like, well, I guess that's sometimes. He's kind of ornery. He's pretty good kid. But when I say well behaved, I'm really talking about statistics. That's what it's amazing how many English words I use for statistics that we'd never use in that context, right? Like, oh, that's an elegant model. Yeah. Right? Have you ever heard that before? Oh, I talk about that. Oh, that's an elegant way of estimating something. Yes. That tells you that I'm deep into the field, or well out of my mind. All right. Model fit. Remember I told you there'd be 9 degrees of freedom? We did the count. There's 9 degrees of freedom. That's good, right? Yes. But based on the likelihood ratio test, and I'm looking at the scaled version, the p-value is 0, right? So the null hypothesis here is that the model is equivalent to the saturated model. The alternative hypothesis is it's not. We reject the idea that it's equivalent to the saturated model. So another way of saying this is our model doesn't fit based on the likelihood ratio test. But that's just one statistic. This next one, does anybody care? Yes, we have at least one correlation that's bigger than 0, that's not equal to 0. That's what it tells us. Now comes the better part. Our CFI, let's go with the robust version, 0.918. Our Tucker-Lewis index is 0.089. Neither of these are good, actually. We want both of these to be bigger than 0.05, not 0.95. Yeah, Yeah, and again, remember root. The word root, as my wife would call it, root. Anybody else say root? It's okay. Root versus root. Um, the root is like a root of a tree. You want it low to the ground, but an index is not a root. So that thing's going to be bigger. Yeah. So anything with an I at the end, you want close to 1, like the Roman numeral I. Anything that's a root, you want close to 0. But these are not good fitting. We don't need to worry about log likelihood information criteria because we only have one model. Let's look at RMSCA though. The robust RMSCA is 0.14, and it ranges, a 90% confidence interval goes from 0.108 to 0.175. And there's no chance of this being excellent fit, and there's a 99.9% chance this is not even adequate fit. So it didn't fit. And then our standardized root mean squared residual 0.056. Now, some people say, well, that looks like it fit. But in the overwhelming evidence of all the statistics otherwise, which are likelihood based, that have a little bit more weight to them, this is not your own, that's your only piece of evidence that it may be close to fitting. And we often don't allow that one. That one's not good enough, usually by itself. So now it's time to kick the computer. This model doesn't fit. Anybody sad about that? Like, just make it stop. I get it. I was a student many years ago. Actually, I'm still a student, just not as much in classroom. So the model does not a good job approximating the saturated covariance matrix. So if we took these numbers and started using them in our reports or our studies, they may be inaccurate. So instead, let's go look at model modification, right? I'm going to highlight this. That gets worse to see. Model information should be guided by theory. You know, one of the pet peeves I have, and I did it in this slide, is a lot of times a statistician say, oh, you need expert judgment, you need theory, you need something that's not statistics to do this. In some ways, that's kind of distasteful, which is like theory is going to solve all your problems. No, theory got us into this mess because we had theory and we built this, right? So that's sort of an odd way of putting a pure numeric process of determining model fit is likely to capitalize upon chance, is likely to sacrifice generalizability. That's the caution there, right? We had a hypothesized model, it didn't fit the data well. We're going to do a little capitalization on chance, but how we capitalize on chance to make this fit may not be, maybe in some ways are worse, some ways are better. But let's take a look at model fit. You'll see at the bottom of my slide there, I have the normalized residual covariance matrix. I'm going to grab that here in code with this line. And the part that I highlighted here was this one. There was a huge residual covariance. Remember, this is normalized, right? These are z-scores. So a z-score bigger than 1.96 or less than negative 1.96 is like a critical value of 0.05. Like, you know, or you can think of this as standard deviations away from where it should be. This one's 5 standard deviations away from where it should be. There are no other numbers anywhere close to that. We have a negative 2.65 here. So this is telling us why model fit is bad is partially due to the covariance between usefulness and math self-concept, and partially due to gender and CC. Course credit hours, yep. So let's take a look at the modification indices. Oh my goodness, there they all are. Ha, the look on people's face. Boom. And you're like, yeah, that's, you told me that's what's going to help me get out of my model fitness. Yeah, where? You know. All right, let's go on the slides here. I narrowed it down a little bit here. Okay. In a path analysis, when you've observed your variables, adding a residual covariance is the least amount of harm. Because what you're saying is, there's a part of my model that I'm not accounting for, but I'm not going to make a claim as to the direction of the effect, right? If the place where I had a problem was this usefulness versus math self-concept covariance. There's three ways I can fix that. One way is a direct effect of usefulness on math self-concept. One way is a direct effect of math self-concept on usefulness. One way is a covariance between the two of them. In this case, we call it residual covariance because both of them are endogenous variables. So when you think of the direct effect, what are you claiming there? You're saying that for instance, if I predict math self-concept with usefulness, you're saying that someone's perceived usefulness of mathematics directly impacts their self-concept. You basically dictated the causal direction. Even if this is not causal data, hypothetically speaking, that's a causal statement saying usefulness impacts it, and it's in this direction. The flip of that, if I take math self-concept and I predict usefulness with it, you're saying math self-concept causes usefulness, increase in usefulness, or changes usefulness. Again, very strong statement. The third path, a residual covariance, does neither of those. It says, yeah, I don't fully explain both of these variables. Yes, there is a covariance between them, meaning I don't explain them in the same or opposite directions, but I'm not making any claim as to what that alters the causal order of a model or what I'm hypothesizing is an effect. I'm basically saying my model is not fully accounting for how far off we are on both of these variables. It's a benign, sort of looked at as a benign way to improve model fit. Benign meaning you're not making strong statistical claims for your model. Does that make sense? It's funny because all three of these are equivalent models, but when you put one in one way versus another, it's thought of as bad. Let me say it again. You are, but you're doing the same.
If you're doing confirmatory, you just broke your rule of I'm not changing what I am doing as I'm analyzing the data.
Right.
Whereas if you change the covariance, it's not doing anything, it's not breaking your model. You're just saying I want to let this.
I'm not accounting for more variation or covariation than I expected, is what I'm saying. And yes, I'll repeat that. Okay. If we look at usefulness in MSC, what you're going to see down the modification indices are very large values, right? There is a 41 here. Now, this is a double tilde. So that means this is the residual covariance, meaning if we added it to the model, we would expect the likelihood ratio test to change by this much, and the value of the parameter would be 70.9. Okay? But take a look a little bit more. We will see these two variables again. Here's usefulness in MSC. All right, this is saying that if we take MSC and use it to predict usefulness, it's going to have roughly the same value, same size. Now it has a bit different parameter estimate. That's because it's units of MSC, or units of usefulness per units of MSC. Right? And then we have a third one right here. MSC tilde usefulness. These three numbers are all trying to remedy that cell that had the normalized residual of 5.51.
Is it common for those to be, so I'm looking at it like the MSC, the variance,
Mhm.
that's the single to the.
That would be a regression slope, a direct effect.
Okay.
Yep.
Okay, so when we're looking at some of these numbers, I noticed that like the use to MSC and the MSC to use are the same.
They are the same, you're saying? Yes. Yes. Yeah. Oh, yes. So, yeah, they're all trying to do the same thing. And this one's so 41.517 and 41.517 are identical. This one's off a little bit, and that's what happens. There's a lot of calculation that goes into these numbers, so the precision is not exact with it. But each of these each of these values, the covariance up here, and then each of these direct effects, right? This one, and where'd it go? Where's the big number? This one right here, right? They're all trying to do the same thing. They're going to remedy that cell that had the normalized residual of 5. But these two, the regression slope version, come with it with the idea that you now have a much different model to describe, right? Because what you're saying is this effect is happening, these regression versions. Whereas the covariance is simply saying, yeah, my model didn't account for their covariation after I residualized these. But I'm not saying why. It just happened.
Can you say the preference for that two regression one?
Yeah.
Regression ones again?
It sounded like I said that good. I don't know if I remember it. Just kidding. I don't know if I say anything good at this point.
Regression is con added.
Yeah, so these two right here make a very, very big change to your model. Think of it this way. If I added MSC to predict usefulness, now my other slopes for usefulness will change most likely because MSC will be related to them. But I'm also saying, no, usefulness is being caused by MSC in a hypothetical level. And what this down here is saying, MSC is being caused by usefulness. Right. Well, no. So here, the bigness of the number says we need to do something with that. Right. That's the one saying, yeah, this one is going to solve our problem. Right. But the conceptual idea as to which one of the three to pick is the following. Either of the regressions makes a very substantive change to our model. Very substantive. Whereas the covariance is a minor change. Because we're not claiming that usefulness is being caused by math self-concept. We're saying something is going on that we're not accounting for both variables. Yes. The 40. Yeah, let me try it again. The number 40 shows up on here. This is telling you, hey, look here. 40 says you need to add a parameter. One of these parameters is going to be good to add. Now, which one? Which one is, do I do it as a direct effect or do I do it as a covariance? What's that? Which decision am I making? I make the decision. Pardon? So my rationale is the following, right? If there's a strong theoretical basis for why this could be the case, it makes sense, right? But I don't have that. I'm not in this field. I don't have that theoretical basis. So I'm going to say the one that says, yeah, the model didn't account for what being off on both of these, and I don't know why. That's what the covariance says. Oh no problem. No. I'm sorry. I'm doing a bad job. My job is to help you explain it, and that's what I'm going to do. What's that?
I asked you to repeat it. It's been off the rails since
No. This is a really hard concept, though, right? Right? And this is what I'm more than happy to repeat. I'm more than happy. This is like when I was in your chair, lectures have gone by, right, before I could figure this out. So, but just think of it. I mean, when we add a variable in a regression, that's a really strong statement, right? It not only impacts that variable, it impacts other variables on that regression as well, right? But when we add a variable as a covariance, we're just sort of saying, I don't know why, but I need to account for it. That's basically it.
There's no interaction. We didn't have a covariance. Just saying there is interaction.
So I try to stay away from that term because it's a loaded. That means something else usually. Yeah, I wouldn't go there. So interaction is usually two variables affecting another. So I try to stay away from that term, but I will say these are all related. And that's why these numbers all show up. And because what you see on the left-hand side and what you see on the right-hand side are the same, they're all pointing at fixing that covariance right there. Okay? How we doing? It's tough. Good. Not good that you're not clear, but you would think. Yeah. You've got a great point. Mathematically, they're equivalent, right?
Can I add something? I think this would help. So we're going with the ice cream analogy. Adding the covariance would be like adding sprinkles. It adds some color, it adds some decoration, but it doesn't change the ice cream side itself. But when you change, yeah, against it. But when you add a regression flow, that's essentially like, I'm going to call it ice cream, but it changes the nature of like the story you're telling. So it would be, you would have to make a theoretical assumption in your.
So after that, going on the line, how is this like the formula, right? Are different based on if you go back to like
So here,
like slide number, read the overall size, that one.
is it this one right here? Oh, the equations. This one right here. This one right here? Oh, so on this one, if we added the regression slope of MSC on usefulness, it would show up on this line right here. Alternatively, if we put usefulness predicting MSC, it would be on this line. And then finally, the residual covariance can't even be shown here. And that's part of it. You can think of it this way, right? You can't show it here because it shows up in the residual side, and that's literally where what's happening is forming is coming through. Does that help?
That's just an operation.
Can I help? Can I help answer? Sorry.
It's just like operation notation. We're looking at.
Oh yeah, the double these things right here. Yeah, it's Lebanese, right? It's its own version of a language. Yeah, when you see one, remember the Leban syntax, right? When you go to the Leban syntax, oh come on, Jonathan. All right, right here. The Leban syntax, to define a regression slope, you only needed one, and to define a covariance, you needed two. And so when you look here, this operation two is like if you were to write that in syntax, that would be a covariance, whereas you write this in syntax, it would be a regression slope. Does that help? Okay. This is a really complicated. It's ridiculous, right? But okay, so think of it this way: when you have observed variables, the least harm theoretically to fix is the residual covariance, because it's a less strong statement about changing those regression lines, right? That flips in factor analysis, because it actually weakens one of our core assumptions about measurement. I'll get to that in a few weeks. But for now, when you have observed variables in your model, a residual covariance between them simply means when I do my prediction of these two variables, when I predict usefulness, when I predict math self-concept, how far off I am is related between both of them. Like my offness on usefulness is related to my offness on math self-concept. I can characterize or quantify how far off they are with this, but I'm not making a strong statement as to why they're off, just that they are. If you look at, I know this is probably a terrible topic, but I'm going to say it. Election prediction in the United States. 2016's election was not a good one when it comes to presidential politics for prediction. I'm not making political statements yet. You have to wait for me when I'm not professor when you want to hear political statements. Okay? Fair, yeah, that last day. Yeehaw. No, I'm still hired somewhere else, so. Not quite. But I will say, not to talk about the actual politics, to talk about the science of trying to predict it. In that election, what had happened was the polls had thought Hillary Clinton was going to beat Donald Trump in the presidential election. It was like a 65% chance. It didn't happen. And when you looked at some of what had happened was when you made predictions state by state, there were correlated residuals between them. And that correlated residual sort of indicated, yeah, we were not accounting for something in data that was similar to it that could have been there. Now, what that had not been accounted for are the low propensity voters that turned out in that election and happened to vote for one of the candidates. That's usually what had happened, right? So that residual correlation is a tough thing to unpack. It describes a systematic trend that you're not fitting your model well. It has evidence as to what you could do in future studies to try to remedy. But for this study by itself, because we don't have any other variables to put in this model, the residual correlation, residual covariance, does the best job of parsimoniously saying improving model fit without putting strong statements as to the direction of why it misfits in place. Does that make sense? How's that sound? Residual covariance is a crazy concept. It is, but when you see it, it tells you, hey, I really got to figure out why I'm off in the same way on these two variables from this model. What didn't I collect that caused someone's perceived usefulness and someone's mass self-confidence once I predict them to be off similarly, right? Just like, why did I predict Pennsylvania one way and Michigan another way, and I was off on both in the same direction for them, right? How's that sound? Yeah. Sorry, can you repeat the question? I'm sorry. Yeah, we want to reduce misfit, right? Right. Yeah. Yeah. No. So interestingly, here, if we don't account for this, its impact will show up in subtle ways in other places in the results we do have. Right. And I'm running out of time this week. In fact, I'm out of time this week. Next week, I will show you this. A model that doesn't fit is likely to have a bias when it comes to your estimated parameters, and a similar bias or even bigger bias for your standard error. And it's sort of error induced by model fit. So we need to achieve good model fit to have a confidence that these numbers are somewhat accurate. But what our model is telling us is we're not getting good fit. So we need to account for why we're not having good fit, and then we can start thinking these numbers are accurate. Does that answer your question? All right. We're out of time now, but I'm happy to answer your questions after class, although we have another one in here at 3:30. But after or in the hallway afterwards as well too. Thank you all for coming. Next week I will have more the remainder of this lecture, and we'll have another lecture about factor analysis. So homework 2 is out now, but it's due in 2 weeks. You don't have to start it yet. We can talk about it later. But yeah, that makes sense. Absolutely.